Dear Group 1, my name is Aaron Heisman, and I'm joined by my teammates Alejandro Trevino, Sofia Burdell, Felipe Perez, and Maria Garcia Chinchilla. This is our presentation on system identification and controls. The objective of this lab is to create a controller for a hypothetical DC electric motor. To do this, we investigate a brushed DC motor model and look at the nonlinearities in the system. We use time and frequency domain identification techniques to characterize a brushed DC motor, and we solve a problem to get a better understanding of time and frequency domain analyses. For this lab, we're working with a sample robotic arm, and we need to determine if it's suitable for operating conditions in two cases. One with a voltage of 2.3 volts and a frequency of 0.1 hertz, and one with a voltage of 3.5 volts and a frequency of 15 hertz. This lab is broken up into three parts. In part 1, we used different input voltages and recorded the motor speed response to determine the linear and nonlinear relationships. In part 2, we found the motor constant and time constant by isolating and analyzing the linear regions of input voltage versus speed. In part 3, we modeled the system through Bode plots using motor velocity and input sinusoids to determine the motor and time constants.
In part 1, we will discuss system nonlinearity, which includes determining the motor dead zones and saturation limits. In order to determine the dead zones, omega star was calculated by multiplying omega steady state by 0.632, which is where time over the time constant equals 1. Using this, we can determine the time constant. The linear relationship shown is such that omega steady state is divided by the input voltage, which gives the motor constant Km. With these constants, we can now find the ranges of the dead zones and saturation limits. To characterize dead zones, this is essentially nonlinear behavior. When the system is running very slowly, there appears to be little to no response. This can be attributed to the lack of voltage to overcome the static friction to turn the flywheel. The Km value can be used to evaluate this behavior, since Km is the slope of the omega versus input voltage. When this Km value is not consistent, that linear relationship is violated between omega and input voltage. Based on the plot of the motor constant versus the input voltage, it is observed visually that Km is consistent from 2 to 6 volts. Therefore, the dead zone occurs below 2 volts, and the saturation limit occurs above 6 volts. The effect of a dead zone causes the input voltages to have little to no response from the motor. In other words, within the dead zones, the input voltage cannot overcome the static friction to generate a response. The effect of a saturation zone causes increases in input voltages to no longer cause an increase in the steady state value of omega or the velocity of the flywheel. Overall, both of these zones affect the operating range of the motor.
Next, we are going to talk about the second part of the lab, time domain system identification of the given data. In order to best see the plots for the omega versus time, the data was grouped in ranges from 0.01 to 0.1 volts, then 0.1 volts to 1 volt, and finally from 1 volt to 10 volts. In this slide is the plot of the omega versus time for the Vn values ranging from 0.01 volts to 0.1 volts. As you can see, the omega is 0 for the input voltages at 0.01 volts and 0.02. This lack of change in position might be because of the voltage is so low that the motor really struggles to overcome the static friction, and also accounts for the oscillations around the steady state of the graph. Next is the plot of omega versus time for voltage inputs spanning from 0.01 volts to 0.1 volts. In this plot, you can see that as the input voltage increases, the response is clearer and steadier. This slide contains the plot of time versus omega for input voltages ranging from 1 volt to 10 volts. In this plot, you can see that the omega values increase as the voltage increases, but they are very close to each other for the Vn equals 8 and 10 volts. The disturbance in the output at 4 volts, the yellow line, may have been a data collection error, so the steady state value was calculated using the omega values after 2.5 seconds for all of the input voltages. In order to understand what range of the omega steady state to do with the linear regression, the plot of the input voltage versus motor gain was used. We chose a range from 2 to 6 volts, as you can see inside the red circle on the leftmost plot, and as the red points on the right plot.
This plot shows a step response for only the linear range from 2 volts to 6 volts. The motor time constant was found by averaging the Tm values for the linear range, which gave us a value of 0.0868 seconds. The composite value for the motor gain, Km, was found by using a linear regression fit, which gave us a value of 9.1157. Once zoomed in on the omega versus time plots, if you look at when the response reaches steady state, you can notice that there are tiny continuous oscillations. This occurs because the axis of rotation may not be directly concentric with the shaft, or there may be tiny mass on the outer edge of the shaft that will induce a torque once it's rotated. The main differences you can see between the theoretical and experimental plots is that the theoretical has a steady state that is slightly larger. This may be because we had to attenuate the range to make sure it was linear to calculate Km. Since we used larger Vn values for our range, the motor gain constant is good for modeling higher voltage inputs. The theoretical model also does not oscillate. This is because the motor time constant, Tm, is a constant, so that inertial term will not be varying as discussed in the previous slide. When the mass was added to the flywheel, K and M remain basically the same value of around 9.06. This was expected because to calculate Km there are no factors that account for the mass shown in the motor gain equation. However, since the motor time constant does have an initial term in its equation, once the mass was added to the flywheel, the time constant increases. If you look over to the time plot, you can see how the response with the mass reaches steady state much later than it would have if it didn't have that extra mass.
In part 3, we will discuss the derivation of Bode plots, as well as a calculation of both the motor and time constants using these plots. So to construct a Bode plot, the input and output of waveforms of frequencies ranging from 0.1 Hz to 10 Hz are analyzed for the magnitude and phase lag at each frequency. The calculated values are shown in the table. An important trend to note in the table is that as frequency increases, the phase lag phi increases and the output amplitude b decreases. This is due to an inverse relation between omega and the magnitude b over a, and a proportional relation between omega and phase lag. These can be seen in the formulas listed below the graph. So this next slide demonstrates the experimental Bode plot derived from the data in the previous slide. The corner frequency, which is located at the negative 45 degree phase angle, and the negative 3 dB drop is located to be at 8.625 radians per second. With this corner frequency, the time constant was calculated to be 0.116 and the motor constant to be 12.19, as shown on the formulas in the slide. These values differed from the constants previously derived with time domain techniques because one set was calculated in the time domain, while the other was calculated in the frequency domain. Additionally, there may have been a lack of points near these corner frequencies, leading to error in the calculation of the time constant, which also led to error in the calculation of the motor constant. Overall, though, some of the advantages of using the frequency domain over the time domain is the ability to better visualize the signal at these different frequencies and the ability to demonstrate phase shifts, in contrast to the time domain, which is better for demonstration of transition responses. In this slide, the experimental plot is compared to the theoretical plot. From these graphs, you can conclude that the assumption of a first-order system is valid since the experimental plot matches the first-order theoretical plot to an extent. Some of the initial assumptions, such as negligible inductance and friction, may have led to small discrepancies between the two. So, in the conclusion, we will discuss which of the two cases presented in the problem statement would give an accurate representation of the motor response. So, in case 1, the voltage is 2.3 volts and the frequency is 0.1 Hz, which is roughly 0.62 radians per second. Both of these values fall into the appropriate ranges to get an acceptable motor response for both the time and frequency domain. The signal will most likely not be in a dead zone, nor will it be attenuated. In case 2, the voltage is 3.5 volts and the frequency is 15 Hz. Based on the ranges of acceptable inputs, we see that the voltage 3.5 volts falls in the acceptable voltage range of 2 to 6 volts. However, in the frequency domain, it is apparent that the 15 Hz, which is approximately 94 radians per second, is way past the corner frequency, meaning that the signal may be attenuated. So in conclusion, case 1 would be a much better representation of the system since it meets both the voltage ranges and the frequency ranges.